officially introduce Richard. So yeah, it's a pleasure to introduce our first speaker, which is Richard Thomas from Imperial College London, and he's going to be speaking about refined sheaf counting on local K3 surfaces. Yeah.
Great, thank you, Vicky. Thanks very much for the invitation. So yeah, if you're online and you missed the explanation of those pictures, then tough luck. Okay, so I'll begin. So I'm going to work throughout with a K3 surface, and I'm going to work with this Calabi-Yau threefold, or local Calabi-Yau threefold, called the local K3, which is just the total space of the canonical bundle of the K3 surface. And we're going to count, in some sense, compactly supported sheaves on this Calabi-Yau threefold. So they're going to have rank 0, right? Because they're compactly supported. They'll be torsion sheaves. And they'll be allowed to be semi-stable because of Dominic's work. We can do that. I'll explain that. And they're always going to have a fixed Mukai vector or churn character, whichever you prefer. And that'll be denoted V. It doesn't matter which you use. We're going to use the C star action on the fibers of the canonical bundle to refine everything by working equivariantly. So I will explain this Nekrasov-Okounkov refinement. But this will turn all our numbers that we get by counting into Laurent polynomials in a variable t to the half. T is the standard weight 1 representation of C star, which are actually invariant under t to the half goes to t to the minus the half. Actually, they're not Laurent. No, they're rational functions. Rational functions, t to the half. And then the plan today is to compute all these invariants for all classes V, all multiple cover, so all multiple classes, all strictly semi-stables as well as stables. For these theories, which are all intricately related, we'll focus mainly on Vafa-Witten theory, which might sound a bit niche if you've not got into Vafa-Witten theory, but more or less, as I'll explain, it's exactly the same as something called reduced DT theory, which is the appropriate sheaf counting theory here. So it doesn't really matter which of these you use. Stable pairs contain slightly more information than the others. And then the reason is it's just a good illustration of all the tools that we now have, which, 10 years ago you could only really have computed one of these invariants for primitive Mukai vector, but now you can compute everything. Okay, and obviously that's an exaggeration, so I don't really use the degeneration formula, although in a previous paper with Davesh Malik, where we do all these computations for unrefined invariants, we were forced to use the degeneration formula, and dimension reduction is another thing we use there, which I don't have to use this time. And the reason is that wall crossing formulae and technology has improved a great deal since we wrote that paper, and now we can apply it directly on this non-compact Calabi-Yau threefold, rather than working on a compact one like S times an elliptic curve and then degenerating it to S times a nodal curve, a P1, which is what we had to do before. So there are two techniques we don't have to use. Also, I'm not going to use motivic integration that Dimitri was talking about on Friday. But otherwise, more or less all computational techniques go into these calculations. Okay, and then my whole talk is on this next slide, so it's a bit dense, I apologize. I take my time with this. And then the actual talk will be just about giving more details about each of the bullet points. So I'll start by just reviewing or defining very vaguely what these invariants are, what the reduced obstruction theory is, and Joyson pairs. These are things which are used to, when you have strictly semi-stable sheaves, possibly with many automorphisms, so you have a stack, you can stabilize that stack and soak up those automorphisms by picking some kind of framing. So the thing we use is Joyson pairs. So that's, you pick certain sections of your sheaves, and then that that gets rid of the automorphisms. And then counting those is equivalent to, that gives you a way of counting the semi-stable sheaves. I'll also briefly review this Nekrasov-Okounkov twist. And then I'll get into how we actually do the computations. So the first thing we do is we C-star localize. So all our sheaves collapse down to some thickening of this surface S. But they'll only be set theoretically supported on S. In general, they'll be supported on some thickening of S. So if it's a one-dimensional sheaf, for instance, it might be supported on a curve in S, but thickened. Now, how do I draw this? That's an infinitesimal thickening there, as you can tell. Thickened in the C direction, scheme theoretically, sort of D times, let's say, and some art. So basically you would take some sheaf on S and tensor it with an artin ring, C of X over X to the D or something, in the C direction. So that will reduce the computation to such sheaves. And now, if your sheaf is constant in this thickening direction, so if you just taken a sheaf, pulled it back to X times C, and then chopped it off at, by dividing by X to the D, so it's completely constant in this X to the D direction, then your moduli space of such sheaves is really isomorphic to the moduli space of sheaves on S. And although the counting is not the same as the counting on S, they're clearly related, and you can compute the relation between them, and that gives you a multiple cover formula. So sorry, that's the first acronym. You get this multiple cover formula, which tells you how these thickened sheaves, the counting of those relates to the counting of the thin sheaves just supported on S. And it's a 1 over D squared, a multiple cover formula, as I'll explain. And then co-section localization, which I'll also explain due to Keem and Lee, I think Keem's here, shows that nothing else contributes. So if you instead thickened in some other way, which was still C-star invariant, so maybe you've got another bit of your sheaf here, and maybe that's thickened but less, but by a different amount. So that I wouldn't call that uniformly thickened, because the thickening is different on the two pieces. That's also a C-star invariant sheaf, and you can prove that, as I'll explain, they don't contribute. So everything reduces quickly to a computation via a multiple cover formula, to a computation of sheaves supported scheme theoretically on S. So that reduces the complexity enormously. And then this is the other acronym you have to learn for this talk. So there's multiple cover formula and wall crossing formula. So the refined wall crossing formula, due to recent work of Joyce, Henry Liu, and Kuhn, Liu, and Tim, who's here, and derived equivalences of the K3 surface, means that we can do a derived equivalence of sheaves on the K3 surface and change our Mukai vector from one counting some rank R sheaves to one counting rank 0 sheaves. So we can really get down to just dimension 1 sheaves on the K3 surface. So we're just changing the Mukai vector to another Mukai vector of the same square and divisibility. And as we do that, that messes up the stability condition, and then you have to wall cross through the space of stability conditions to get back to a sensible Giesecke stability condition or slope stability or something. So that reduces everything to counting dimension 1 sheaves. And then why does that get you anything? So this is part of a general principle. People know how to do computations with stable sheaves on K3 surfaces. So that was all the 90s, 80s, 90s. That was you anyway, and your mates. So we know there you can do derived equivalences and deformations to turn any moduli space of stable sheaves on a K3 surface into a Hilbert scheme. So you can turn the sheaves into ideal sheaves of points. You can't, that's no use when you're allowing strictly semi-stable, so you need another paradigm. And the one we use here is to turn everything into dimension 1 sheaves. And the reason that's an advantage is that then you count these dimension 1 sheaves, possibly strictly semi-stable, by taking their joists on pairs. So now what you have is a dimension 1 sheaf with a section and a certain stability condition. And what you can do is you can change that stability condition until you get something called stable pairs. So they're also dimension 1 sheaves with a section with a different stability condition. And I will explain what those are. And the reason that's good is because stable pairs have fantastic property if they're on a surface, any surface, which is that their virtual cycle can be computed because more or less, and in the case of K3 surfaces more, it's really true, stable pairs on a K3 surface, the moduli space can be expressed, it has a global Kuranishi chart, so that it can be expressed as the zero locus of a section of a vector bundle over a smooth ambient space, which is explicit. And so that means you can actually, you're in the very rare situation where you have some control on the virtual cycle, you know what it is. It's the Euler class of this bundle on this ambient space. And you can't do that with, more general sheaves on K3 surfaces, but you can do it with stable pairs. Okay, and so we can really compute the virtual cycle as an Euler class, and that means you can do computations, and very quickly you do these computations on these ambient spaces, you can push back down to a Hilbert scheme of points again, and then this method of Ellingsrud, Gurcher, and Lane from the 90s turns these integrals over the Hilbert scheme into integrals over the product of copies of S instead, and therefore integrals over S. And what that gives you, from old work with Martin Kuhl, is it shows you that the answer depends on only intersections of the self-intersection, let's say, of your Mukai vector on the K3 surface. It doesn't depend on the divisibility of the Mukai vector. So what that means is you can replace the Mukai vector by a completely different one of the same square, but which is now primitive. And you can do the computation there and you get the same answer. So now you're back to primitive classes and you're back to the 1990s, you're back to computing with stable sheaves. So everything reduces to Hilbert schemes of points. You have the constraints of hyperkähler geometry and all of Mukai's results. And so you can really do the computations. And indeed, those computations in the stable case were done by Kawai and Yoshioka a long time ago. And that gives you the result. So this is the whole talk in some sense, and I'll just give more details about each bullet point as I go. But they'll all be self-contained little talks. So if I lose you, you can refocus when I move to the next bullet point. Are there any questions?
What's a stable pair?
Yeah, that's all coming. All of those things are going to be defined.
So I have a quick one. So I guess 1, 2, 3. And so in point 4, there's this cartoon picture you drew of getting rid of the non-uniformly thickened.
Yeah.
Don't you also use that in some other place to get this divisibility state, independence of the divisibility of the curve path?
Can you ask? Can we discuss this at the end of the talk? Yeah. But yeah, sort of. I might answer that. We'll see. Okay, and then just for fun, I'll tell you the formula. So these are the final formulas. So as I say, we'll focus on Vafa-Whitney invariants, but it's more or less equivalent to DT invariants. So what it says is there's a multiple cover formula. So the Vafa-Whitney invariant in class V is a sum of contributions of D times thickened guys. So this term here, this summand, is the contribution, if you cross out the red, of the D times thickened sheaves. So you start on S with Mukai vector V over D, and then you thicken it D times, and you do the computation, and this is the answer you get. So you get this 1 over D squared multiple cover formula. So the sheaves on S, when you thicken them up d times, they contribute a 1 over d squared multiple cover formula. And then the contribution on S is given by what it would be in the stable case, which is a certain Hertzebruck genus evaluated at t to the d. So let me explain what all these terms are. So the first one is this refinement of the integer d. So this is this quantum integer. So if you set t equals to 1 in this, you just get d. But this is the refined version. And then this chi hat is this normalized Hertzebruck genus, which refines the Euler characteristic. If you put t equals 1 in this, you get back the Euler characteristic. Okay, but this is something just coming from the Hodge theory of S.
Are we somehow restricted to square negative v? It looks like v squared should be negative, so that exponent is not negative.
Yeah, it does, doesn't it? Sure, I think it might be v squared over 2d squared minus 1. I think there might be a minus
that would make
missing.
a lot more sense.
Yeah. This is quantum, man. Yeah. Okay.
So you said it didn't depend on divisibility, but there's a divisibility.
Yeah. So what doesn't depend on divisibility is the computations on S, and that's the computation on S.
But the answer itself does.
But the multiple cover formula makes it depend on divisibility. Yeah. Okay. And then the hard bit is the computation on S. On S, you're counting semi-stable sheaves, and the claim is that actually you get the same answer as if you were computing stable sheaves, which it reduces to a normal Hilbert scheme of points on S. Or moduli of sheaves on S, you should always think of as just Hilbert schemes of points, stable sheaves. Okay, so the hard bit will be showing that this is the right answer. The multiple cover formula would just be a localization computation. So that'll be the formula, and then these Hertzebruck genera of Hilbert schemes of points on a K3 surface were computed by Gutscher and Sergel, again, a long time ago. And their generating series is a Jacobi form, whatever that is.
Is there a kind of BPS version of this which doesn't have divisibility?
Yeah. I mean, those are the BPS numbers. Yeah. All right, and the other formula that we're aiming for, and again, I will define what a stable pair is in a bit, is for refined stable pair invariants. So again, there's a refinement of these integers, and they have a different multiple cover formula. It's a 1 over d instead of 1 over d squared, but it's very similar. And then here's the divisibility thing that Dominic was asking about. So it turns out this invariant, just counting stable pairs supported on S, depends only on the square of the class you're in, the curve class beta. So if I call that square G, that determines a genus G, which is the arithmetic genus of curves in this class beta over D. Then I can form a generating function of these numbers, and they're determined by another hideous, well, amazing, beautiful, beautiful, there you go, Kawai Yoshioka product formula, and that's the formula. And you can tell stable pairs contain slightly more information because it's a slightly worse formula. Okay, but some substitution in here gives the previous formula. All right, so whatever, there's some formulae. All right, so now we begin. So I'm going to define each of these things. So first I'll assume that we're in the case where everything's stable. So let's say primitive Mukai vector or Chern character. All right, so this is an old story. When you do deformation of sheaves on a Calabi-Yau threefold, you have this symmetry that the obstructions are dual to the tangents. Okay, so deformations of sheaves are given by x1. Obstructions to those deformations lie in x2, and those two are said dual to each other. All right, and that gives you some geometry in this situation. There's an obvious deformation for these compactly supported sheaves, which you just translate them along the c direction. And what that's dual to under this duality is this trace map. So this is a famous object in the obstruction theory. So if you haven't seen this before, one place you can get obstructions to deforming sheaves is you could deform the K3 surface itself. If you deform the K3 surface itself, the Chern character or Mukai vector which is of type PP, Hodge type PP, because it's algebraic, might cease to become of Hodge type PP. So the 1-1 class, the divisor class, might pick up some 2-0-2 cohomology. And this, what happens is if you deform the K3 surface in that way, all of your sheaves will be obstructed. They will not deform with the K3 surface because your class is no longer algebraic. So associated to that deformation, there will be an obstruction, a non-zero obstruction in here for your sheaf E, and its trace will be that class. It will be the 0,2 component of the Mukai vector of your sheaf on the K3, on the deformed K3. As you deform the K3, this Mukai vector picks up some 0,2 cohomology, and this is it here. Okay? But if you don't deform the K3, or if you only deform the K3 in the Noether-Lefschetz locus so that your Mukai vector remains algebraic, then all the obstructions will lie in the kernel of this map. And we're going to remove this piece. So this piece forces all sheaf counting invariants to vanish on a K3 surface. And that's because, you know, when you do enumerative geometry, you get deformation invariant answers when you use virtual cycles. And you can always deform so that your Mukai vector is not algebraic, it's not of Hodge type. And so suddenly all your moduli spaces become empty, so all your enumerative invariants must be 0. So we fix this by doing reduced sheaf counting, which means we remove this piece of the obstruction theory, and now you have a chance for all your invariants to be non-zero, but only deformation invariant on the Noether-Lefschetz locus. Okay, so we're going to remove both. First, we're going to divide the moduli space by translation. That removes this piece, and then we're going to remove this from the obstruction. And that means we'll still have a symmetric obstruction theory of virtual dimension 0. And that therefore gives us invariants. And the invariants are given by the localization formula. And working equivariantly, you might get, you've localized the equivariant parameter, you might get a function of t and t inverse. Because the virtual dimension 0, it turns out you just get a rational number. All right? So in this way, you get enumerative invariants and they're rational numbers. And in this setting of K3 surfaces, which is slightly simpler than more general surfaces, this is the appropriate Vafa-Witten invariant. Now, we want as a refinement of this, and what Nekrasov and Okounkov tell you to do, motivated by physics, is to twist everything by the virtual canonical bundle, the square root of the virtual canonical bundle of the moduli space. So what you do is you work K theoretically into the cohomologically. So you take the virtual structure sheaf, which you should think of as roughly speaking the structure sheaf of the virtual cycle. You twist it by this line bundle, and then you take holomorphic Euler characteristic. Now, because we're in virtual dimension 0, the line bundle is trivial on the virtual cycle, and so this doesn't do anything. This gives you back the same invariants. But they're just expressed in a different way. They're expressed as the holomorphic Euler characteristic of a line bundle on this 0-dimensional virtual cycle. All right, but this makes sense in higher virtual dimensions. It makes sense in physics. It's turning, you see, if you didn't have this line bundle, you'd be doing something like the virtual Todd genus, and this is turning it into the virtual A-hat genus. So the Todd genus depends on the complex structure, and it's not relevant to the physics, whereas when you do this twist and you turn it into an A-hat genus, that no longer depends on the complex structure. You're turning the index of the D-bar operator into the index of the Dirac operator. So that you can imagine that might be relevant in physics. And how it's relevant here is we can now take into account the t dependence. So we can now work equivariantly and do all this equivariantly. So what we do is we take the equivariant version of holomorphic Euler characteristic, which means we just remember the C star action, And so we turn this index into a character of C star. Okay? So instead of taking the Euler characteristic of this graded vector space here, we take its C star character. So if we write this graded vector space, if we remember its C star action, we write it as a sum of weights, and then it's a virtual vector space, so minus another sum of weights, then chi t is given by the obvious formula. All right, so we just work equivariantly, and now because of this twist, we get something non-trivial. And this is not particularly sophisticated, but it's conjecturally related to the cohomological refinement of DT theory. And Pierre de Coombs proved that in the compact case, but this is a non-compact case. Okay, I won't say more about that. Okay, but this turns out to be the right thing to compute. And it's due to the virtual Serre duality of Fantecchi and Goetscher, it's invariant under this transformation. It's also invariant under deformations, which keep you in the Noether-Lefschetz locus. So your Mukai vector remains of type 1,1. I want to just give you a feeling for this thing. So the special case of where your sheaves are just supported on S, and there are no semi-stable sheaves, so maybe your Mukai vector is primitive. In that case, it's very easy to compute these invariants. All right, so what you find is that the moduli space is smooth. It's obviously not zero-dimensional. It's deformation equivalent to a Hilbert scheme of points on the surface. It's hyperkähler. But it has considered as a moduli of sheaves on this Calabi-Yau threefold, it has a non-trivial obstruction bundle, and that's the cotangent bundle of your moduli space, tensor with this character and shifted, because that is an obstruction bundle. It's in degree 1. All right? And so what you find when you compute the numerical invariant is the 1 over the virtual normal bundle contribution gives you this, and you end up with the Euler characteristic. All right? So sure, most of you are familiar that DT invariants you can think of as, roughly speaking, being Euler characteristics of moduli spaces. So this is a shadow of that. So in this case, the Vafa-Witten invariance is just the Euler characteristic of the moduli of sheaves on the surface. And then the refined version, you can compute that as well. You work out the virtual canonical bundle. You see it's the actual canonical bundle of the moduli space squared, so it has a natural square root. And then you work out what this refined Vafa-Witten invariant is, and it's as follows. So the virtual structure sheaf is just the Cazole complex on the dual of the obstruction bundle. So that gives you this term. It also gives you a load of t's. I can't see where those are. Oh, those are here. Anyway, there may be some t's missing. I apologize. And then you've got this square root of the virtual canonical bundle. That gives you this term. All right, and then so you've got all these wedges of the tangent bundle, but you're tensoring with the canonical bundle, so they become complementary wedges of the cotangent bundle. That gives you a sign, and then that gives you this thing. But so you end up with holomorphic Euler characteristics, well, C star characters, of all these wedges of the cotangent bundle, and that's precisely what the Herzebruch genus was. So I apologize for this clash in notation between equivariant index and Herzebruch genus, but as you can see, they're closely related anyway. So what you find in this case is that the Vafa-Witten invariant is the Euler characteristic, and the refined Vafa-Witten invariant is just this normalized Herzebruch genus. And again, I've made this sign error that Jim pointed out, I think. No, it depends. Oh, no, it's fine. The square of the Mukai vector computes Homs minus x1s plus x2, so it's minus the virtual dimension. Yeah, that's right. So the squares of the Mukai vector should be negative. So they're not the squares you're thinking of. The squares of the curve classes are minus this. In fact, yeah. So it's your fault.
Sorry, my bad.
You're saying the instanton contribution doesn't have divisibility.
Right, so at the moment, of course, I'm working in this simple case where it's really stable sheaves and V's primitive. And I get this answer, so there's, yes, correct. What we will prove is that this is true for any V, so even when V is a multiple of another V, this is still going to be true. But as we'll see. That's sort of the hard bit. All right, so this slide was just to give you a feeling that roughly speaking, some invariants are Euler characteristics, others are refined to be these normalized Hertzebruch genera. Now, when you have strictly semi-stable sheaves, what you do is you stabilize them, get rid of their automorphisms by taking their Joyce-Song pairs. So this is where you replace the sheaf by a pair, sheaf plus section, and the stability condition is the sheaf is semi-stable, but the section does not factor through any semi-destabilizing subsheaf. All right, and that turns out to be a good moduli problem, proper if the moduli space, if the geometry is proper and so on. And then you do all the same stuff again. It has a natural symmetric obstruction theory. It has that has these two parts, translation and the co-section, which we remove. So it turns out that the obstruction theory and the deformation theory is all governed by this complex, this two-term complex you make from the Joyce-Song pair. And deformations of this complex are equivalent to deformations of the Joyce-Song pair. All right, so again, we get this symmetric obstruction theory, and therefore we get invariants, and we get refined invariants. So again, we take the virtual structure sheaf, we twist by this square root of the canonical bundle, and we take the equivariant index. All right? And you probably don't have much feeling for that, but in the stable equals semi-stable case, this Joyce-Song moduli space is a projective bundle over the sheaf moduli space, because it just involves a choice of section. And in that case, what you find is that the invariants made from the Joyce-Song pair moduli space are just the Hertzebruch genus of this projective space times by the Vafa-Witten invariants I defined 2 slides ago. And the conjecture that I made, I don't know, 5 years ago, was that in this case, that is true more generally. So you can define Vafa-Witten invariants, even in the semi-stable case, via this formula. So the conjecture was that this formula, which defines these things to be the quotient of that by this, is independent of n, so that these do not depend on n. Okay, so
how does stable stop the projective space from jumping dimension?
Oh, just because n is huge. How do you go back on it? Oh, there you go. There you go. So for more general surfaces, there's a much more complicated formula, but because K3 surfaces have this H2 of the structure sheaf, this H20, the formula is much simpler. So I will explain that at the end if I have time. Oh, I've gone. There we are. And this has now been proved by Henry Liu using this development in refined wall crossing technology. So I will explain this at the end if I have time. But this is now proved. But maybe this formula shouldn't appear so terrible to you just because I've shown you that these Hertzebruch genera arise naturally out of these Nekrasov-Okounkov-refined invariants. Okay, but so this is a true formula, and this gives a definition of Vafa-Witten invariants by counting Joyce-Song stable pairs and then putting them through a very simple universal formula. All right, so these are well defined, and now we can compute them. So we use C-star localization to produce a multiple cover formula. So the simplest C-star fixed locus that we get are these uniformly thickened sheaves. So you start with a sheaf on S, you pull it back to X, you pull it back horizontally in my picture, and then you just tensor it with the structure sheaf of D times S, all right? And this gives you a whole component of the C star fixed locus of the moduli space of sheaves up to translation. And then when you compute what the contribution is via the deformation obstruction theory and the virtual normal bundle, what you find is that you get a 1 over D multiple cover formula for the pairs invariants, and then putting them through that universal formula, that gives you a 1 over D squared multiple cover formula for the Vafa-Witten invariants. I forgot to say earlier on, Vafa and Witten define invariants via a PDE directly on the surface. The connection between that and this is you have to go through a spectral construction to re-express things on the threefold and a Hitching-Kobayashi correspondence. But Vafa-Witten theory turns out to just be sheaf counting in this simple setting. Okay, so that's really all there is to be said. I'm not going to do the computation, but it's not particularly a hard computation. Okay, and so what you find is that these uniformly thickened parts of the moduli space contribute this to the Vafa-Witten invariant. So for every divisibility of the Mukai vector, you look at sheaves supported on S, you take their contribution and you divide by this D squared, this refined D squared. All right?
So the instanton contributions don't care about divisibility, and divisibility contribution is all about monopole.
That's what we need to prove, absolutely. So the whole talk, in some sense, is about proving that these do not depend on divisibility, but of course these do. And so what we have left to show is there's no other contributions, and then we have to compute these and show they're independent of divisibility, as Dominic said. Okay, so why do the other terms not contribute, like the one I've drawn over there? So this is this double cosection argument. So this is a strange construction if you've not seen it before. So what you do is there's a certain flow you can define. Here, this is it just schematically on the moduli of sheaves or pairs. What you do is you start with a thickened guy and you pull off the last layer. So you should imagine this is like Cx divided by x to the d. And then what you do is you replace it by Cx divided by x to the d minus 1 and another copy of Cx divided by x. Okay, and you flow this copy off, you translate the last layer of the sheaf off in the C direction, you leave most of the sheaf alone. All right, so you can define that rigorously, and then you can differentiate this flow at t equals 0 to get a vector field on your moduli space. And here's the miracle. This is, if you don't spend your life doing Artinian ring geometry like I do, then this is a big surprise. Amazingly, this vector field is the same as this vector field on these uniformly thickened sheaves. So if there was no red bit, so if we took a uniformly thickened sheaf, like in this picture, this vector field you get from this flow, so peeling off the last layer, is the same thing to first order in T. That flow is the same thing as just moving the whole sheaf at a slower speed along the C direction. Okay, so you shouldn't be happy with that. That should be a surprise. But it's this computation, which you know very well. So this here is the equation just in the C direction. I'm ignoring the S direction here in this computation. But in this computation, in the C direction, x is the variable in C, t is time. Then this computation you know very well. So this is the equation cutting out this picture. So you have a d minus 1 thickened fat point and a single point at x equals t. And to first order in t, that is the same as this, which means you've got a d times thickened point, but you've just moved it, you've translated it 1 over d times as fast. Okay? So to first order, this flow, the first order in time, this flow only sees the center of mass of this Artinian object. It only sees the flow of the center of mass, which flows at this speed. Are there any questions about this?
So are we working on the space where we divide it out by translation, or you're?
In a bit, yeah. At the moment, just yeah, that's right. So when we divide out by translation, this does nothing, right? So in other words, this deformation doesn't do anything to first order. This vector field will become 0 when we work on modulo translations, and that's the key. All right. So we get this vector field, but on the uniformly thickened locus, as Jim's pointing out, this vector field is the vector field we've already used and which we've already divided out by. So it doesn't give us anything new. But on the other components of the moduli space, where we're not uniformly thickened, it is not proportional to the vector field we've already used, because it's kind of proportional up here with constant of proportionality 1 over d, and it's proportional down here, but with a different constant, 1 over 2 or something. So it is not globally proportional. All right, so dual to this vector field, because of this symmetric obstruction theory, we have an obstruction, a cosection. We have a map from the obstructions to C. And on the uniformly thickened locus, it's 0, because remember we've already, we've already removed this piece of the obstruction space in our theory. So this new vector field gives us the same one, so it is 0. But it's non-zero on the obstruction space precisely for all the other components. Okay? So what you have is you have this obstruction bundle or obstruction sheaf over your moduli space, and you know the virtual cycle is something like the Euler class of that obstruction sheaf. But if this obstruction sheaf has a section which is nowhere vanishing, that Euler class vanishes. And it doesn't quite have a section, it has a cosection, but that's okay, that just means its dual has a section. That also means its Euler class vanishes. So this nowhere vanishing cosection here, over that whole components of moduli space, they force the invariants to vanish. So they force the virtual cycle to be 0 and 0 contribution. So are there any questions about that? That's kind of a key point. Okay, so we've got rid of all the other contributions now. So now via the multiple cover formula, we've reduced everything to computations just on S. So now we can use autoequivalences. So this is how, in the old days, you would now try and convert your sheaves into ideal sheaves of points. We're now going to convert our sheaves into dimension 1 sheaves supported on curves. So Toda did a lot of this work, and then the refined wall crossing formula, because as you do this autoequivalence, you mess up the stability condition, and you want to move back to a better stability condition. So this refined wall crossing formula then allows you to assume that actually your Mukai vector is the Mukai vector of a one-dimensional sheaf. And then further wall crossing and shows you that the invariants actually count in Joyson pairs of one-dimensional sheaves are determined by stable pair invariants, suitably refined, also counting one-dimensional sheaves, but in a slightly different way. So this answers Michael's question. So we're now counting stable pairs with a different stability condition. So again, what we have is a dimension 1 sheaf, but instead of asking that it be semi-stable, we ask it has pure dimension 1. So it doesn't have any zero-dimensional subsheaves. And then instead of asking that the section doesn't factor through any semi-destabilizing subsheaf, we ask that the section has zero-dimensional cocurve. So this is a different stability condition on pairs. But again, there's a wall crossing formula to tell you how to turn counting Joyson pairs to counting these stable pairs.
So can
Yes.
So all these wall crossing formulae are trivial, so there is no contribution.
Yeah, that's the thing I want to explain at the end. If you shut up. Okay. So then the other miracle, the other cool thing, is that stable pairs on a K3 surface are really cut out of a smooth ambient space by a section of a vector bundle. So there's something like this for any surface, but it's much more complicated. But for K3 surface, it's super simple because the moduli spaces of curves on K3 surfaces are just smooth linear systems because H1 of the structure sheaf of the K3 surface vanishes. So what happens is a stable pair is basically a curve. That's the support of the stable pair. So that lies in a linear system, which is just a projective space. And then it's a bunch of points on that curve, which are the co-kernel of the section. So if you remember, a stable pair was this sheaf with a section, but it had zero-dimensional co-kernel. So it's basically a curve that lies in here, and a bunch of points on that curve. So what we do is we embed it in the space of all points on the surface, that's the Hilbert scheme, times by this linear system, and then we cut it out as an incidence locus that we ask that the points lie on the curve. And then it turns out that this is actually a scheme-theoretic isomorphism. This incidence locus is this space of stable pairs. And it's cut out by a tautological section of a tautological vector bundle. And, okay, this is the kind of thing that if you go away and work it out for yourself, it'd be much better than reading it on the board. But at a point, if you take a subscheme, Z is some collection of endpoints. Sigma is the section of the line bundle cutting out your curve in beta, okay? So this is a section of a line bundle. This is a fat point. This is endpoints. And the incidence condition is that sigma restricted to Z should be 0. So it lies in this vector space. Now, as you let that vary over this ambient space, this vector space becomes a vector bundle, and these elements of this vector space become a section. All right? And so the two miracles, one miracle is this stable pairs space scheme theoretically is this incidence locus. The other is that its obstruction theory, given to you by all this Vafa-Witten nonsense, is the obstruction theory you get by seeing it via this Kuranishi chart as being cut out by a section of a vector bundle. So even though it's singular in general, so when beta is divisible, for instance, this space will be singular, this section of this vector bundle won't be regular. It doesn't matter. The virtual cycle is still what you expect it to be. It's the Euler characteristic of this vector bundle on this ambient space. All right? So you can really compute. All right? And the virtual structure sheaf is just the Cazul complex on this, the dual of this vector bundle. Okay? So you can really compute. And me and Martijn did, and we did it in the more complicated case of a general surface. And what you find is that you get integrals over this ambient space here, and then you can push them down to this factor, and so you get integrals over the Hilbert scheme. And then Ellingsrud, Goetcher, and Lane tell us how to turn those into integrals over the product. And so finally you get integrals over the surface. And so what you find is that the answer depends on only these integrals, these intersection numbers, not the divisibility of beta. And so this is like this is basically equivalent to this chi independence conjecture that lots of people work on, of Joyce and Toda. Okay, so we can calculate with primitive beta, and then by deformation invariance with irreducible beta, curve class beta. So what we do, you don't do the computation that you set out to do, you replace it, you replace your beta by a completely different beta of the same square, but which is now primitive, different divisibility. All right, and the computation, the answer is the same, and because you've done that, now all your moduli spaces are smooth, everything's stable, and the computations were done long ago by Kawai and Yoshioka, and they give you the answer you want. Okay, so is that really the correct time? It's 10:02? Okay, okay, so so that's the end of my talk. Now I can describe the wall crossing formula. Are there any questions?
No, relativiscopic sleep
I think that's very appropriate. Beautiful timing. Okay, so I used this wall crossing technology. So I just wanted to explain what the development was in wall crossing technology, which made all of this possible. So I'm going to go back to the simplest possible wall crossing, and I'm going to compute things with old style Euler characteristics and pretend that they're DT invariants. All right, so now let's suppose we're on a compact Calabi-Yau threefold, and we're counting sheaves E, and let's suppose my E sits inside an exact sequence like this, where A and B are stable, and that we can vary the stability condition so that the slopes of A and B cross. So the slope of A might be is less than the slope of B, so that E is stable. But we're going to vary the stability condition, and as we do so, the slope of A is going to become bigger than the slope of B, and so that's going to destabilize the sequence. But I'm in the simplest case, nothing else is going to happen. So A is not going to become unstable during this process, neither is B. A and B are in different classes, they're not isomorphic, they're not the same. So let's suppose we're in that situation. So just below the wall, the E will be stable, and just above, it will be unstable. But extensions in the opposite direction will become stable. So on wall crossing, we lose this space of extensions star, and we gain the extensions in the opposite direction. And, well, so let's compute what happens to the Euler characteristic. So it's going to change by minus the Euler characteristic of this, plus the Euler characteristic of this, so that's this thing. And then by Serre duality, that's actually this thing. So you're getting an alternating sum of extensions from B to A. And there are no HOMs from B to A, because on the wall, A and B have the same slope and they're both stable. And as you know, by the Schur property of stable sheaves, if there was a homomorphism between them, they would be isomorphic. So there's no HOMs, therefore there's no x3s by Serre duality. There's no negative x, so there's no higher x bigger than 4. So what you find is this alternating sum, this is all the x, so this is actually topological. This is given by a Riemann-Roch formula, and it's the so-called Mukai pairing of B and A. So this is just a topological number which only depends on the Chern characters of A and B, or the Mukai vectors of A and B. And then what we do is we integrate this computation over the space of A's and B's. So for fixed A and B, your numbers, your enumerative invariant, your Euler characteristic, is changing by this topological quantity. And now as you vary A and B, you have to take the Euler characteristic of the moduli space of A's and the moduli space of B's. And so what you find is the invariant, J stands for Joyce, the invariant changes above the wall, it equals its value below the wall plus the correction. The correction is given by this topological number times by the Euler characteristic of the moduli space of A's times the Euler characteristic of the moduli space of B's. And then the moment you go to more complicated wall crossings, you'll get more complicated Harder-Narasimhan and Jordan-Holder filtrations. So instead of just A and B destabilizing, A itself might be destabilized, so you end up with these long filtrations and iterated extensions, all right? And what they give you, so you should always think about what happens on the wall. On the wall, this E sort of splits into A plus B, and that's reflected in this quadratic term in Joyce and DT invariants. When you have more complicated wall crossings, you now get cubic terms. You get J of sort of A1 and A2 and A3, where E is splitting into those. That's the graded piece of the filtration on the wall. Okay, and then if you have length 4 filtrations destabilizing you, then you go to a quartic term and so on. But in this simplest case, there's no dot, dot, dot. But in general, you get these quadratic terms, then cubits and so on. But they're all of the same form. They they're preceded by a universal topological constant, which is very hard to compute, but it's universal and it's topological. It only depends on the Chern characters. So that's the wall crossing formula as it stood 10 years ago, due to Joyce and Song, Kucevich and Soiberman. But now there's a better wall crossing formula which doesn't use these Euler characteristics and bare end weighted Euler characteristics anymore. It uses virtual cycles. And that has a huge advantage for us, as I will try to explain in the last slide. And then there's a K-theoretic version using virtual structure sheaves, and it also allows you to use C-star equivariant invariants, which we couldn't do before. Okay, and so this is this work of which hasn't appeared yet, but this work of Kuhn, Liu, and Tim. And what happens in this wall crossing formula is these Euler characteristics that I had before. Look, let me remind you. This was an Euler characteristic of a projective. This came from an Euler characteristic of projective space. So this constant here. This gets refined to the quantum integer. So it gets refined to be the Hertzebruck genus of projective space, which is just the quantum integer n instead of the standard integer n. And so what you find is you get a wall crossing formula of this kind of shape. You get refined invariants on both sides, and you get this quantum integer instead. So that has the advantage that we can apply this in non-compact settings now, so that's good. We can apply it directly to our Calabi-Yau threefold, but it has one bigger advantage. So let's suppose that we're counting all our sheaves. Sorry, E became F. I'm not sure how. This is E or F and A and B. If they're all counted, instead of counting them with their full obstruction theory, with X's, we count with their reduced obstruction theory, where we reduce this translation and its dual. Then what we find is on the wall, you see, this object A plus B, it has two copies of this H2OS in its obstruction theory. So from the X's of A's and the X's of the B's, we get two copies of this. But we've only removed one of them. So what you find is that the other one kills all the invariants. So what you find is in this situation, this quadratic term vanishes, and so do all the higher order ones. And you just end up with this trivial wall crossing formula. So what you find is in lots of situations, you can just wall cross all you like, and you always get the same invariants. And I've used that, but that's been hidden in what I've been doing. But the other situation is that you might count A without removing this piece, but F and B could be counted in the reduced Vafa-Witten sense, where you've removed this piece from their obstruction theories. So I'll give you an example of that in a minute. And then in that case, what you find is you get the quadratic term, but you don't get the higher order terms. So why is that? Because that should be obvious. What have I done? So I've removed, yes. So if I remove one copy of this group, which is just a copy of C on a K3 surface, I remove it from all the obstruction theory of F and B, then I might think, well, but I've got two copies of it here, but that's okay. I'm counting A without removing it. So I'll explain how that could be done in a second. So that still contributes. But then once I go to the cubic term, there's three copies, and so immediately everything vanishes. Okay, so the example is when I'm computing stable pairs or Joyce-Song pairs, I'm computing with this complex. And this complex is not compactly supported anymore. It's supported over the whole threefold. Okay? What happens is when we compute with this complex, we do remove that H2OS term from the obstruction theory of our compactly supported sheaf and from the complex. I did that on my slides. But we don't remove it from this line bundle over the whole of X. All right? So that still, it turns out that when you compute with this, you don't remove this term, and you still get a non-zero answer. And why is that? That's because if you take a line bundle pulled back from the surface and you translate it, it's still the line bundle. So you no longer have this translation acting on the moduli space. All right? It acts trivially on the moduli space because this line bundle is supported on the whole of X. So actually, you should compute that without removing an H2OS term. And when you do, you get 1. Okay? So in that case, what you find is the following wall crossing formula, which is how I'll end. You know, there's a wall crossing you can do in a space of stability conditions where above the wall, all these extensions are stable and they give us Joyce-Song pairs. And below the wall, there are no extensions, so you get 0. And so the wall crossing becomes the following. You get the invariant. Above the wall is the invariant counting Joyce-Song pairs that I used. Below the wall, you get 0. Then you get this normalized Hertzebruch genus from the projective bundle, projective space. And then you get a 1 that counts this guy without removing, without taking reduced obstruction theory. And then you get the invariant counting the sheaves E. Okay. And so this is the wall crossing formula that Henry Liu proved, that I used on a previous slide. And then there's a similar story by taking n equals 0 for stable pairs with a slightly different stability condition. But the moral of this is none of this works when you use bare-end weighted Euler characteristics. When you use virtual cycles, this H2OS is a very powerful thing, and it leads to all kinds of vanishing, and it really simplifies all the formulae and so on. So it makes life much better. Okay, I'll stop there. Thank you.
Are there any questions?
So say that you want to compute any elliptic version of these invariants. Would this structure work similarly, or everything just breaks down?
Yeah, I would think this works fine. I would think, I don't immediately see anything that would go wrong. Yeah. Yeah. So you should do it.
Yeah, Balash?
So the wall crossing is sort of a threefold phenomenon, at least the way you presented it. But in your scheme, it seemed that wall crossing also happened on the surface when you did these derived equivalences, and you said that there was some derived equivalence that messes up the stability condition and the wall cross. So kind of, in actual fact, all these computations are pulled back to the threefold so that you can...
Yeah, they're all, it really is a three-dimensional phenomenon. Yeah. So when you have sheaves on the surface, you have to push them forward to the threefold and compute using that obstruction theory. Yeah.
So the H1 OS being trivial, they only showed up in one place.
Yeah.
So if you replace S with like an abelian surface, do you expect that, like, how serious is that generalization?
I think that bit's okay. You'll still be able to prove divisibility, independence of divisibility, because me and Martijn did those computations. So I think that'll be okay. But then the analog of the Kawai-Yoshioka formula, yeah, that's probably fine. People know how to count on abelian surfaces. Yeah, I don't know the answer to that. Who's ever thought about abelian surfaces? Yeah.
You have to worry about translations on the abelian surface as well.
Right.
You want to divide out by that. So
by that.
More.
Right, so you have to dual, you have to divide by the dual abelian surface. Yeah, I mean, there is some theory here.
So with Shandy, we did some computations on that, but this was just an Usher thing. But you can at least for the Euler curve, you can do something.
Yeah.
But I don't know, it's not quite as much.
Right.
I think there's another question on the back. Yeah.
When you're like turning it into like a one-dimensional sheaf just before you go to stable pairs, in the case where you have like trivial wall crossing, it's fine. But like in this case when it's not trivial, do you have any control over what you're changing, or does it stay in the same chamber?
No, that's quite hard. I swept that under the rug. That's buried in work of Toda. The wall crossing is non-trivial. But I don't want to go. I didn't want to go into it. It's quite complicated. Yeah, it's a good point. Well spotted. Damn you.
So one question. Maybe you lose what's interesting about here, but if you go to a compact Claviau geometry that's fibered by K3s, and you try and do sort of fiber-wise invariants, say in non-primitive classes, can we compute everything there, or is that already? I think.
And it's not clear. You would have to take the cohomological refinement and then specialize to the Herzebruch genus refinement, and none of these methods that would naively work. You'd have to, be much harder. But by of course, the cohomological refinement's not deformation invariant, so you have problems. But if you could prove it was in this situation, you could deform the deformation to the normal cone of the K3 fiber where all the action is, right? Because you're taking some twisted K3, right? So, and then suddenly you're in K3 times C, and you can start to use this. But I don't know if you have such deformation invariance. Yeah.
So even already on this case, can you try and compare I guess you're getting refinement from the C star action, right, but then there's some other refinement that you get from cohomological.
Right.
Understand the relation.
And then there's some kind of virtual de Rham theorem which relates the two.
Do we have that?
Yeah, so Pierre de Coombe can prove that in the compact case, not in this case, and it's probably not true in this case, actually. So there's work of Davison and Meinhardt computing cohomological dt in some cases for this geometry, and they get a 1 over d quantum d multiple cover formula. So they don't get 1 over quantum d squared, they get 1 over d times quantum d. So almost certainly the two theories are not identically the same. Yeah, because it's non-compact.
Are there any questions online? I mean, if so, you should just unmute yourself and ask the question. I think no, we gave them their opportunity. Okay, then I think we'll thank Richard, and you can come and ask him more questions during the coffee break.